We're going to talk about molecular bonding, which is different from what we saw in ionic compounds, because in ionic compounds you've got a metal and a nonmetal, and the metal tended to lose electrons and the nonmetal gained those electrons. In molecular bonding, we have nonmetals and only nonmetals. So what they have to do, because neither of them are losing electrons, they have to share electrons. So here's an example of a molecular compound that you probably are familiar with, and that is H2O. So this is what H2O looks like. H2O is water. So if you see here, oxygen and hydrogen are both nonmetals. There's two bonds, or there's two ways that electrons are represented here. The one is as a line. And in this line, you should sort of imagine, anytime you see this line, that you're looking at two different electrons. One that's closer to the hydrogen, and one that's closer to the oxygen. In reality, they're both hanging out a little bit closer to the oxygen, but I just want you to understand that for every line that you see for a bond, there's two electrons. Same thing here. If there's a line, you're looking at two electrons. And then the other way that electrons are represented are as lone pairs. So each pair of electrons that you see that are drawn out separately are what we call lone pairs. And these lone pairs, we're going to look at how you would determine whether or not you need lone pairs when you're drawing the structure. So a molecular compound will have lines to show bonds, as well as lone pairs to show electrons. So electrons can be in these bonds, so that for every line there's two electrons. Say, for example, you see a double bond. So a double bond between two different elements will have 1, 2, 3, 4 electrons. Again, because each line is 2 electrons. Let's say you have triple bonds. Triple bonds have 1, 2, 3, 4, 5, 6 electrons. Again, we'll take a look at examples where we see these. So let's start with a compound like this, NH3. What you will have to do is draw what we call the Lewis structure for this compound. In order for us to do that, we have to see how many electrons we have to work with. And we only get that by looking at how many valence electrons are in each of these elements. The reason why we only look at valence electrons is because those are the only electrons that are involved with the bonding. So these are the electrons that are on the very outside shell. So in order for me to see how many valence electrons each of these elements has, I just have to take a look at my periodic table. Nitrogen is in group 15, which means it has 5 valence electrons. There's only one of the nitrogen, which means that it only contributes 5 electrons. Hydrogen, because it's in group 1, has 1 valence electron, and there's 3 of these hydrogens, which means that it contributes 3 electrons in total. So if I add these two up, I get 8 valence electrons that are involved in the bonding of this particular compound. Once I've figured that out, I'm going to start by drawing a general structure for this compound here. And as a rule, I always want to use whichever element there is one of in the center. And because there's only one of nitrogen, I'm going to write that first. All of the other compounds can be written around this particular element. So I only have hydrogens, and I've got 3 hydrogens. So I'm going to draw 1 hydrogen here, 1 hydrogen here, and 1 hydrogen here. So I've accounted for all of the elements that I have here. And I have 8 electrons to work with in terms of bonding. I'm going to start by drawing single bonds between the elements in this structure. So if I take a look at, I have 8 to begin with. I used up 1, 2, 3, 4, 5, 6 of these as single bonds. So after I've done that, I want to subtract. So I'm taking away the 6 because I've already used these in the compound. And 8 minus 6 is 2 electrons. I've got 2 electrons left over. Now, usually what you would do is take however many electrons that you have and try and put them on the elements that are on the outside so that they have a full 8 electrons. However, hydrogen is an exception. Because it's in the first row, it only has one shell. And if you remember back from grade 9, the first shell of that Bohr-Rutherford diagram only holds 2 electrons. So hydrogen is happy with the 2 that it's bonded with. So each hydrogen has 2 electrons already. So I don't need to add on more to any of these elements. So after I've looked at the outermost elements, I have to look at my central element. How many electrons does this have? So it has 1, 2, 3, 4, 5, 6. And I've got the 2 left over, so I'm going to add these as a lone pair. Now, if I take a look, hydrogen, this hydrogen is happy, this hydrogen is happy, this hydrogen is happy. They're all happy because they have 2 electrons. This nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So that is happy as well. Now, there's a way for me to confirm whether or not this is the correct structure. And that method is called formal charge. And formal charge involves taking a look at the charge for each element in the structure. So I have here nitrogen. So let's start with nitrogen. Before I do that, let me write you a general formula for what I have to use in order to find the formal charge. So I have to start off with the number of valence electrons. So for nitrogen, so let me do nitrogen as an example as we go through. So nitrogen started off with 5. It's in group 15, if you remember. Then you have to take into account the structure that we've drawn here. You have to take away the number of electrons that are involved or associated with this element as a lone pair. So there's 2 electrons here in this lone pair. Okay, so you're subtracting 5 minus 2. And then you have to take into account number of electrons in bonds divided by 2. So in this case, I've got 1, 2, 3, 4, 5, 6 electrons as a bond divided by 2, which is 3. So if I take a look at my formal charge, 5 minus 2 minus 3 is going to give me 0. So that tells me that nitrogen has a formal charge of 0. Then let's take a look at hydrogen, and I'm only going to take hydrogen once, because if I look at the way that hydrogen is bonded, they all look exactly the same, right? They all have one single bond. So if I take the formal charge of this, I already know the formal charge of this hydrogen and this hydrogen. It would be the exact same. So starting with the number of valence electrons, 1, minus the number of lone pairs, which it does not have, which is 0, minus the number of electrons that it is bonded to as bonds, divided by 2. So 1 minus 0 minus 1 will give you 0. So now that I've confirmed that each of these elements has a formal charge of 0, and that the entire compound also has a neutral charge, there isn't a -1 or a +1 near there, I'm happy to confirm that this is the correct structure. Let's take a look at an example like carbon dioxide. Again, as I've done previously, I'm going to count the number of valence electrons. There are 4 valence electrons in carbon. There is 1 carbon, so carbon contributes 4. There are 6 valence electrons in oxygen times the 2 oxygens that there are. 6 times 2 is 12. This gives me a total of 16 valence electrons to work with. Whichever one of my elements there's only one of, I'm going to write in the center, oxygens on either side. I'm going to start by adding single bonds connecting the elements together. So I'm going to account for these in my electron bank. So 1, 2, 3, 4. So the 16 that I have started off with, I used up 4 for single bonds, which I have 12 electrons left over. If you remember from the previous example, I always have to start off with the elements on the outside. I didn't do that for hydrogen because they were already happy and stable. So oxygens, because these are not, I'm going to add my 12 electrons to both of these oxygens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I've used up all of the electrons that I had to start off with. Now let's take a look to see if all of my elements are happy. So oxygen here has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Remember, this one line means 2 electrons, and both carbon is accounting and sharing those 2 electrons as well as the oxygen, right? So carbon has the 2 and oxygen has the 2 as well. So they're sharing those 2 electrons. Carbon has 1, 2, 3, 4. So if it has 4 electrons in total, it's not completely happy. Now, I can't just add a double bond if I wanted to make it 8. What I would have to do is replace one of those lone pairs. So take one of those lone pairs away and then add a double bond. So let's try doing that. So if I take away a lone pair here, and then if I add a double bond, so now carbon has 1, 2, 3, 4, 5, 6. Let's confirm that that doesn't change the number of electrons that this oxygen has access to, which is 1, 2, 3, 4, 5, 6, 7, 8. So I would need to do that on this side as well in order to make my carbon satisfied. So I took away that lone pair, and then I'm adding this as a double bond. So remember that you're not just adding double bonds just as you wish. You have to take away a lone pair and then put a double bond in. That helps you keep track of the total number of electrons that you have to work with in your compound. So just to confirm, carbon has 1, 2, 3, 4, 5, 6, 7, 8. So do each of these oxygens. Now, as we did previously, I want to make sure that this is the correct structure. So I'm going to use what we call formal charge. I'm not going to write the formula out this time. I'm just going to go through the numbers pretty quickly. So carbon has 4 valence electrons. It has no electrons as lone pairs. And it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonds divided by 2. So this gives me a formal charge of 0. Oxygen, I'm going to take a look at both of these oxygens. They look identical, which means that they have the same type of bonding, which means that I'm happy to check the formal charge of just one to give me the formal charge for both of them, because you know that it's going to be the same. Oxygen starts off with 6 valence electrons. It has 1, 2, 3, 4 electrons that are as lone pairs, and 1, 2, 3, 4 electrons in bonds, so 4 divided by 2. So 6 minus 4 minus 2 will give me a formal charge of 0. So oxygen here has a formal charge of 0, carbon has a formal charge of 0, this oxygen has a formal charge of 0, which means that this is a stable compound, and I'm happy with this structure. Now for this third example, we're going to do the exact same thing. So sulfur has 6 valence electrons. There is 1 of it. And fluorine has 7 valence electrons. There are 6 of them. So it is 42 electrons. If I add these two numbers together, I get a total of 48 valence electrons in my bank of electrons to use from. Sulfur is the element that there is 1 of, so I'm going to put that in the center. And I'm going to surround my fluorines all around it. I'm going to first start by adding single bonds to connect the elements. And I've added 6 bonds, which means there are 12 electrons. So 48 minus 12 will give me 36 electrons that are left over. Remember, when you have these electrons that are left over, I want to start with the outside. So I'm going to start by counting up to 36 so that all of these fluorines are happy. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So I've added all of the electrons that I had from this compound. Now let's take a look to see if all of these elements are happy. The fluorines are all bonded the exact same way, so I just have to check for one to see if it is satisfied. So there are 1, 2, 3, 4, 5, 6, 7, 8 electrons for each fluorine, so each fluorine is happy. Now if you take a look at the sulfur, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. So that's more than what we'd think, right? Because you know that all elements have to fit to the 8. However, this is the compound that you're given. It's SF6. There's no other way to bond it other than this, right? So let's confirm with our formal charge to see if this makes sense. So if I take the formal charge, I only have to take the formal charge of sulfur and one of the fluorines because the charge of all of the fluorines is the same. So let's take a look at sulfur. It starts off with 6 valence electrons. There are no lone pairs. There's no electrons as lone pairs. And there are 12 electrons that are bonded as single bonds and divided by 2. So 6 minus 6 is going to give me a formal charge of 0. Sulfur starts off with 7 valence electrons. Each sulfur has 1, 2, 3, 4, 5, 6 electrons as lone pairs and 2 electrons as bonds. So 7 minus 6 minus 1 is going to give me a charge of 0. So even though this structure shows that sulfur can have more than 8, that is correct because of this formal charge. So you always want to make sure that you do all of these steps first. So do all of this first and then try and satisfy to make sure that the formal charge is consistent. So even though this is seems like it is wrong, it is correct because the formal charge of all of the elements is 0. And there's no other way to bond it other than this. Okay, so let's take a look at a polyatomic ion. So in this, the first thing that is different about these ions is that there is an overall charge. And we'll come back to that when we talk about the formal charge. So let's count all of the electrons that are there for this ion. So nitrogen has 5 and there's only 1 of it. Oxygen has 6 and there's 3 of them. So this gives me 23 electrons, valence electrons. Now what I have to do is account for this overall charge of -1. If you remember back to ions, if something has a charge of -1, that means it had gained an electron. So I'm going to add another electron to our mix. So we will have 24 electrons. Say the charge was -2, it's not, but if it was, I would add 2 to make it 25. But since the charge is -1 for nitrate, I'm going to add +1. So I've got 24 electrons to work with. I'm going to do the same process that I did earlier of drawing the element that I have only 1 of in the center, all of the others around it, and then do a single bond to attach or connect the elements together. And I've drawn 6 electrons in single bonds. So 24 minus 6 gives me 18 electrons. And I'm going to start with the elements on the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So now let's take a look. My oxygens are all happy because each of them have 8. My nitrogen has 1, 2, 3, 4, 5, 6. So I need to make sure that this nitrogen has a full 8. So let's do that by erasing one of the lone pairs and then drawing a double bond. So after having done this, this tells me that nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. I just want to confirm that this oxygen also has 8, which is 1, 2, 3, 4, 5, 6, 7, 8. So this seems to be the structure that I end up with. All I have to do is check for formal charge. So you always want to start off trying to make the element in the center, or all of the elements, have a full octet of 8, right? So you want to start off with that before we deal with any exceptions or any cases where it can fit more than 8. So try and fit up to the 8 and then see what the situation tells you to try and change it up. So in this case, I've got nitrogen. So let's check the formal charge of nitrogen and then take a look. There's 2 different types of oxygen. One oxygen has 2 lone pairs and 2 bonds, while the other 2 oxygens have 3 lone pairs and 1 bond. So I have to check the formal charge for both types of oxygens. So let's check it for the nitrogen first. It starts off with 5 valence electrons. It has no lone pairs, and 1, 2, 3, 4, 5, 6, 7, 8 electrons bonded divided by 2. So 5 minus 4 will give me a charge of +1. Oxygen has 6 valence electrons to start off with, or let's say we're looking at this particular oxygen. 6 valence electrons to start off with. 1, 2, 3, 4 electrons as lone pairs, minus 1, 2, 3, 4 electrons bonded divided by 2. So 6 minus 4 minus 2 is going to give me a formal charge of 0. Let's take a look at the other type of oxygen where there's 2 of them. So there's 6 valence electrons. There are 6 electrons as lone pairs and 2 electrons as a bond. So 6 minus 1, so this is 2 divided by 2, will give me a charge of -1. So if I take a look here, I have the nitrogen in the center that has a charge of +1. And each of these oxygens are going to have a charge of -1. This has a charge of 0. So I've got +1 in the middle, -1 here, -1 here. So if I'm asked to take a look at the overall charge of this ion, I have to account for all of these. So if you do +1, -1, -1 into a calculator, you're going to get an overall charge of -1. And I know that this is correct because take a look at my question. Nitrate has an overall charge of -1. So I know that this is confirmed to be correct. In all of the other examples that we did, the compounds did not have a charge. So we wanted to ensure that the formal charge was always 0 for all of those elements. Just like this, carbon dioxide, no charge, which was why all of the elements had a formal charge of 0. NH3, we also wanted a formal charge of 0.